All right, every great software project hits this one critical moment. It's that leap from knowing exactly what a system needs to do to figuring out how in the world you're actually going to build it. Today, that's the gap we're going to bridge. We are diving deep into the art and science of software design.
So, you've done all the hard work up front, right? You've got your requirements locked down, the analysis model is looking sharp, and you know exactly what the user is asking for. But there's still this huge chasm between that perfect document and the very first line of code. So, where do you even start?
Well, that's where we build the bridge. It's time to move from the what, that analysis model you just worked so hard on, to the how. And that how is what we call the design model. Think of it as the blueprint for absolutely everything that comes next. Let's define this properly. Software design is that crucial architectural phase. It's where all your requirements and all the technical realities of the world smash together to form a detailed model of the software before anyone writes a single line of code. It's the blueprint you'll follow. You know, it's such a tempting question, isn't it? You've got a clear use case, you're fired up, you're ready to get your hands dirty. So why waste time with all these diagrams and models? Well, I'm telling you, jumping straight into the code is probably one of the most common and most expensive mistakes a team can make. And here's why. I want you to meet the villain of our story, technical debt. See, when you rush to code without a solid design, it's kind of like building a house without a blueprint. Sure, the walls go up super fast, but you end up with a system that's brittle, an absolute nightmare to maintain, and it's probably going to fall apart the second you try to add a new window. So, to steer clear of all that technical debt, we have to start thinking like an architect. The entire design process is about creating a detailed, layered blueprint that's going to guide the whole construction of your software from start to finish. Thinking like an architect means you design in layers, right? You go from the really big picture down to the tiniest details. So you start with the overall architecture, the main structural plan. Then you define all the interfaces, which is just deciding how every single part is going to talk to every other part. Only then do you dive into each component to spec out its internal logic. And finally, you plan the data structures and the deployment environment where this whole thing is gonna live. Okay, so how do we actually make good design decisions? Well, it turns out there's a powerful toolkit of core concepts we can use. And really, understanding these ideas is what separates a fragile system that breaks all the time from one that's robust and can scale. First up, we have abstraction. This is your secret weapon for fighting complexity. It is literally the art of focusing only on what's essential right now, while hiding all the nitty-gritty details until you actually need to deal with them. And that highest level of abstraction you can have, that's the system's architecture. It's the foundational structure, the skeleton that makes sure everything works together as one coherent, solid system. And you know what? Within that architecture, you're going to run into the same old problems again and again. So instead of reinventing the wheel every single time, you use patterns. These are just proven, reusable solutions that let you build on the collective wisdom of thousands of other developers. One of the most fundamental ways to organize any system is this idea of separation of concerns. It's simple. You don't mix your user interface code with your calculation logic. You keep them separate. By doing that, each part becomes way easier to build, to test, and to maintain down the road. And the way we achieve that separation is through modularity. We're just breaking a massive, scary program into smaller, self-contained modules. This is the key that makes a really complex system something a human being can actually wrap their head around. So how do you make a good module? The trick is information hiding. You want each module to hide its internal messiness from the outside world. It should only communicate through a stable, well-defined public interface. This is what stops a change in one module from causing a ripple effect that breaks 10 other things. When you do this right, the result is functional independence. We're always aiming for modules with high cohesion, which just means they do one thing and they do it really well. And we want low coupling, meaning they aren't all tangled up in each other's business. That combination is what creates a system that's flexible and resilient to change. So if abstraction is the what, stepwise refinement is the how. It's this disciplined process where you start with a very general, high-level idea, and then step by step, you add more and more detail until you finally have something so concrete that a programmer can just sit down and implement it. Now, refactoring is a cool one. It's like tidying up your blueprint after you've already drawn it. You're not changing what the building does, you're not moving any walls. You're just improving the plan itself, making it cleaner, more efficient, and a whole lot easier for the next person to understand. Ultimately, when you bring all of these concepts together, they help us create well-defined design classes. And this is the final deliverable of the whole design phase, a set of complete, cohesive, and loosely coupled blueprints that are finally ready to be handed over to a developer to bring to life.
Okay, so let's take all these timeless principles and bring them into the here and now. What happens when the software we're designing can actually learn and adapt all on its own? What happens when we have to design for AI?
First, let's just level set on the difference here. Traditional software, like your computer's operating system, just follows a fixed set of rules. That's it. But AI-enabled software, like a modern weather forecasting system or a large language model, does stuff that normally takes human intelligence because it can actually learn and adapt based on new data. Now, what's really fascinating about this is that building an AI system often means you're running two development cycles in parallel. You've got one team building the application itself, which looks a lot like traditional software development, but at the exact same time, you have another team developing the AI capability, the data product, like a prediction model. That's going to be the brains of the operation. And that, right there, brings us to the ultimate question. In this new world of AI-enabled systems, with all their uncertainty and their weird dual development cycles, do these old-school concepts like modularity, abstraction, and separation of concerns even matter anymore? The answer is a huge, resounding yes. In fact, in a world filled with complex, adaptive systems, these principles are more critical than they have ever been. Things like modularity, abstraction, and separation of concerns, they're not just old rules from a textbook. They are the essential toolkit you need to architect a future that is both intelligent and reliable. So the real question is no longer if we should use them, but how we're going to adapt them for this next generation of software.